Hello everyone. It's a very great pleasure to have Dan Scolnic here today. Thanks a lot for accepting our invitation. Dan is now an associate professor at Duke University in the USA, and while he did his PhD at the Johns Hopkins University. Dan works on measuring the expansion history through a variety of techniques, particularly Type Ia Supernovae, and is also active in other approaches and is involved actively in measurements of dark energy with Phantom Plus and Dark Energy Survey. Today, he will present the Hubble Tension in our own backyard, DESI, and the nearness of the Coma cluster. Dan, please, you can start when you're ready.
Great. Thank you so much for that introduction. Thanks everyone for coming. I know this is kind of the busiest time of the year for a lot of people, so I appreciate people being here. Yeah, so today I'm going to talk about the Hubble tension in our own backyard. So the kind of main thrust of this talk will be about a new paper that a bunch of us worked on using recent DESI results, but also I'm going to cover a kind of number of other recent papers as papers on H0 and W keep coming out. So while I have the floor, I thought I could talk about some of the other ones too. Okay. So this is how I always explain the Hubble tension, and I know there's been a number of talks about the Hubble tension, so I'm kind of not going to go too much beyond this, but I like to think of it as like a doctor's growth chart where we have the picture of the universe as a baby. We have kind of the picture of the universe today as an adult. And then we have like the doctor's model, which is lambda CDM. And the whole idea is that if everything is working, then if you kind of take understanding of the universe as a baby and you predict kind of how big or how fast the universe should be, or this baby should be expanding when it grows up, you should match what we see today. And we don't. So there's three kind of obvious things that could be going wrong. One is that something in kind of our measurement of the universe very young is messed up in some way. When the measurement today is messed up, or the kind of more exciting one is that our model is wrong in some way. Okay, so I think the kind of the space of like interesting possibilities has really opened up just in the last year. So on like the theory type side, in the early universe, there's a number of interesting possibilities like early dark energy, different neutrino properties, things that you've heard about through various CosmoVerse talks. And then I think kind of what's changed just over this last year is that maybe kind of something in the middle, which kind of I would always say is like the vanilla boring part. Maybe something's going on there. So we now have Type Ia supernova measurements as well as DESI BAO measurements, and they're starting to show some hints of maybe deviations from lambda CDM. And then I'd say on the more local side, things kind of actually look kind of very normal. And actually, this other DESI paper they'll talk about, you heard about from Khalid Saeed, showed actually things are looking kind of quite just normal at the local universe side. So I really want to talk about these two new sets of DESI results. First, about the BAO measurements when you combine them with supernovae, and then about how we can leverage the new fundamental plane measurements that Khaled has talked about. So before I get into Hubble tension, I want to talk about the dark energy W naught WA side for a little bit, because there's been a bunch of discussion, but not too much, I think people have heard from the supernova community about what might be going on. So taking this a little back, the Pantheon Plus, this analysis led by Dylan Brout, we saw hints of evolution of the dark energy parameter, which we parameterize with W naught and WA. And we saw like a 2-ish sigma when you combine with Planck or we combine with SDSS BAO at the time. And we put this in the paper. We said, hey, this is there, but not really sure what to make of it. So since then, as people have likely seen, there's been the DESI results, and DESI, when you combine just DESI with CMB with Planck, you see also something like a 2.83 sigma deviation in the same direction if you combine DESI plus CMB plus different supernova data sets. You get anywhere from like 2.5 to 4 sigma deviation And if you do DESI plus supernova, you also kind of get the same thing. So any kind of two of these three, everything seems to be pulling in the same direction. But at this 2.5 to 4 sigma, kind of unclear, kind of like how strong this evidence is. So there's been a lot of discussion about, well, like which supernova analysis is the best or what's right. So I just want to say a few things about that, since it's a little complicated. Okay, so for the dark energy supernova sample, this really it's a whole new or 90% new high redshift sample. Um, but they basically had the same low redshift sample as Pantheon Plus. So they could this is it's kind of somewhat independent, but if there's like systematics or and if statistical fluctuations driven by the low Z sample, they're not independent. The other thing that's been brought up about the dark energy survey, which is the constraint that's pulling towards 4 sigma, it's the strongest with this union sample in the middle, is that this is a photometrically classified sample. So there's contamination from core collapse supernova. You could see this is a normal Hubble diagram, but there's these light colored dots. These are what are likely not type Ia. So we don't have the spectroscopic resources for these bigger and bigger samples to be sure that every supernova on our Hubble diagram is the good type Ia. So now we do all this kind of fancy machine learning classification. And I'd say that while this is the kind of main thing that makes DS different than Pantheon Plus or Union, I don't think that this is a driving systematic. Like this looks scary, but it's kind of pretty easy to tell what is core collapse and what's 1As. And this systematic relative to others, this is like 10th on the list of systematic. So um, there may be some things in modeling, but I don't think it's actually the contamination that's driving it. Okay, so to tell you kind of what's the same and what's different, so Pantheon Plus and Dark Energy Survey, they both use kind of very similar analysis tools. So everything's simulation based, where you're modeling as best as possible your sample, um, and then kind of correcting your measurements based on these very accurate simulations. Um, for Union 3, they have a completely different approach. This is led by David Rubin, and this does a Bayesian hierarchical method called Unity, and really kind of like it does its calibration different, it does scatter modeling, every possible analysis thing that could be different is different um, in this. However, the data for Union 3 and Pantheon Plus is nearly identical. I think it's like 85% overlap. So Pantheon Plus and Union 3 have the same data, completely different analysis. Pantheon Plus and DS5 year have very similar analysis, but very different data for high Z, but has the same low Z. So I kind of like to say like it's not like you could just combine them and get like root 3 better, because there's so much overlap. I do think, there's more evidence than just one sample by itself, but there's a good amount of work to try to do to like combine Pantheon plus the new data from DS, or understand kind of maybe these minor shifts. Now, to me, I actually see pretty good agreement between the supernova samples, so I'm relatively happy. However, there's a paper that people might have seen is led by George Stathiou, who kind of did a deep dive on trying to understand where these shifts are coming from. And wrote this paper, Evolving Dark Energy or Supernova Systematics. And what he did is he looked at supernovae that were in both the Pantheon Plus sample from DES, as well as low Z samples, um, and in the DS 5-year sample. And he could see, oh, look, there's like a kind of 0.04 mag shift that seems to be from low Z, though it's actually from DS because there's a normalization constant that can float. So it's really driven by the DS supernovae. So the kind of question posed by George is, well, does this mean that DS is wrong because Pantheon Plus is closer to lambda CDM than DS, um, or what's going on. So hopefully in the next month or so, the Dark Energy Survey collaboration will have its own paper that's gone slowly because DS is a gigantic collaboration and everything goes very slow through collaborations. But we can trace this offset into two parts that George sees, as it wasn't totally obvious. So it's kind of it was kind of what we thought it would be, but these things are not the simplest to track. So the kind of the big offset is 0.04 mag, and about half of it, 0.02 mag, is related to what DS feels are true improvements in modeling the supernova scatter and possible redshift evolution. So it's things that DS would not take back. That it seems like things that really were improved. The other 0.02 mag is really kind of due to like apples to bananas comparison of distances of the same supernovae. The thing is that in Pantheon Plus and DS, they use some of the same supernovae, but when Pantheon Plus used them, they used them from a kind of an older DS sample where there is a very strong selection effect in that sample. So since kind of these analyses are really trying to do like ensemble analyses of the whole sample, then for those specific supernovae, it's like, well, you're the highly selected ones. We have to give you a bigger correction. Whereas in DS5 year, it's a much more complete sample, so you don't have to do such a large correction. Now that's only 0.02 mag kind of on average, but it's not kind of something's right or it's wrong. It's that it's very hard to compare the same supernovae when they come from two different samples. So I'd say kind of that 0.02 mag is real, and it seems like an improvement. The other 0.02 mag just seems like things that it's not so obvious how to compare. So in short, there's nothing from the DS side where something's being kind of walked back right now. Now, on the Pantheon Plus side, it's not like we have kind of done the same type of thing of checking exactly how different it should have been if we applied some of the DS things. But my feeling right now is, a good idea is to kind of look somewhere in the middle. But I don't think it's obvious to say, hey, DS is just wrong. Okay, so that's all I'm gonna say about the supernova sample. But just generally, I'll say about W. I still feel like we're in wait and see mode. I think my top thing is that we need more low redshift supernovae. So samples that are upcoming, like DeBase, led by Dylan, or ZTF, which there's a recent data release on. I think that they're going to be really key to kind of tracing this because that low Z sample is the same for all three of these analyses. Okay, so now let me get to HNOT. So you all heard a CosmoVerse talk a couple weeks ago from Khaled, and it's this really amazing paper where DESI is supposed to, its main goal is to do these baryon acoustic oscillation measurements, but what it's amazing at is just getting lots of redshifts. And what it can then do is do its own peculiar velocity survey where it can measure lots of redshifts and then measure distances using the fundamental plane technique, where you're looking at properties of the galaxies or Tully-Fisher relation, and essentially make its own Hubble diagram and measure H naught for itself. So this is like building its own DESI distance ladder, and what kind of was so interesting to me when it came out was that they get a very precise statistical H naught, and the systematic part. If you look at what I've underlined, the systematic due to the fundamental plane itself is quite small, but a giant uncertainty here is due to calibration, and that is because everything is tied to the Coma cluster, and you need to know the Coma distance. Some external measurement needs to say that. So whatever that uncertainty is will just propagate directly through and dominate the uncertainty. So what a number of us realize is that if you can improve this number, which is pretty humongous, then you could immediately get a very precise H naught altogether. Okay, So yeah, I'll just kind of show. I mean, this is to me remarkable. So this is the DESI Hubble diagram, and you can see that like the scatter per galaxy is relatively high, but like even compared to Type Ia supernova Hubble diagram, the number of galaxies is tremendous. So I mean, this is a really, I think, kind of remarkable new Hubble diagram, where if you can calibrate it, then you could very precisely measure the Hubble constant. Okay, so they show this near the end of the paper where they have different variants in their analysis, and they're trying to say kind of what can move the value of the Hubble constant. And kind of first off, what you should note is that I mean, they're getting a high value of the Hubble constant, even higher than like what we get in shoes. Um, but a thing that can move it a bit is if they change that external distance to the Coma cluster that they use. If instead of using it from surface brightness fluctuations, they use a TRGB distance, which is a little bit different. That can move it to like 74 point something. So either way, whether they just take their SBF distance, which is their nominal external distance, and use that, or they replace it, that's really driving their uncertainty. So if one can then derive a better distance to the Coma cluster, which kind of is the anchor for everything, then you can make this better measurement. Okay, so we put out our own paper like a month after that, and really our goal was just to improve that like first rung, improve that distance to the coma that they're using that's driving that uncertainty. And this is just accepted into the AppJ, it's on the archive. Um, but the kind of summary level is that we tried to find a bunch of supernovae so that we can then get a more precise or more accurate measurement of the Coma cluster, and then that'll propagate the whole way through. So I'm going to go through that now. Okay, so it's kind of neat to compare this to the conventional shoes like distance ladder. Just kind of say what's similar and what's different. All right, so for something like what we do in shoes, you have this geometric method that's calibrating like your Cepheids, your TRGB. Then you have these galaxies that have those Cepheids or those TRGB plus Type Ia supernovae. Um, and then you say, okay, that allows you to calibrate the Type Ia supernovae. So now let me go out into the Hubble flow, and since my Type Ia supernovae are calibrated, then you could measure H naught by comparing distances to redshift. Um, for for this kind of new distance ladder, um, what they're doing is they say, all right, we're gonna take some calibrated distance of of the Coma cluster, which is not like it's not like the most special cluster ever. It's just a kind of very nearby, very rich, has lots of galaxies, so it's kind of a very good one to calibrate to. But it's not like particularly unique in some way. So they say, all right, so we're gonna first calibrate. We're gonna first take the distance of the Coma cluster using what they did was the surface brightness fluctuations. Then they're gonna say that will allow us to calibrate our fundamental plane relation. Now, we're going to find lots of galaxies, kind of make our own Hubble diagram out into the Hubble flow. And because our galaxies have been calibrated to the Coma cluster, now we can measure H naught. So you're swapping the fundamental plane for the Type Ia supernovae, and that first kind of rung is coming from SBF. Now, what we can then do is say, all right, instead of going and trying to measure H on ourselves, let's just try to calibrate ourselves the distance to the Coma cluster using supernovae, and then we're just going to slide that in here, where instead of taking SBF, let's take our calibrated Coma distance and then plug that back into the DESI fundamental plane measurement. Okay. So it's just kind of swapping in like that first rung into the distance ladder. Now What one can also do is do this kind of in the inverse way. So one could say, all right, well, let's say that Planck's value of the Hubble constant is correct. Now, you could then say, all right, let's combine this with the DESI fundamental plane Hubble diagram, and then say, what would the distance need to be? What should the distance to Coma be then, given this H naught and given this Hubble diagram? So this is the inverse way, but it's the same. It's just saying if you take Planck's H naught, you take DESI's Hubble diagram, what then should the distance to Coma be? So we could kind of ask both of those questions. Okay. All right. So when we do this, so because the Coma cluster has lots of galaxies will mean lots of supernovae. So we do a big exhaustive search of all the supernovae in the Coma cluster. You can see just kind of in that square box, this picture is what it looks like. So I mean, this is just like a beautiful cluster, and there's been a number of supernovae over the last 15 years or so, when this has been regularly covered. Okay, so then we go through this process of we get the light curves for all the supernovae, we calibrate them, we standardize them, and I'm seeing a bunch in chat. Okay, and we get the brightnesses, and what we do is we standardize the brightness. We're just trying to get to a standardized brightness value for each supernova, and this is what it looks like. So this is standardized brightness just versus supernova, and we could get a mean value for the standardized brightness. Okay, and this is very good agreement. Uh, Almost like too good, but just enough, scattered that it's okay. But kind of very robust mean of what is the mean standardized magnitude of supernova type 1 supernovae in the Coma cluster. Okay, so then what we could do is we can apply the absolute luminosity calibration that we measured and choose of kind of what a type 1a supernova is, and apply that to this observed standardized brightness so that we can get a distance to the Coma cluster. And this is what we get. So in magnitudes, we get like a little below 35 magnitudes, whereas the Planck kind of prediction of what this should be is up here, kind of near 35.2. So just doing this, taking these independent supernova measurements, calibrating their putting in an absolute luminosity, and saying either kind of what is its like distance or its distance modulus, or what's the distance in megaparsecs. You could look either on either y-axis. You could see there's a greater than 4 sigma difference between this Coma calibrated DESI Hubble diagram and the Planck prediction. So this Planck value is doing that inverse way of saying, given Planck's value of the Hubble constant is correct, and given the DESI Hubble diagram, what should the distance to Coma be? And that's over 110 megaparsec. So I mean, this is kind of pretty amazing that it's replacing a number of steps of the kind of normal shoes-like distance ladder, and getting just by itself 4.2 sigma from Planck. Now, this was our way, which is kind of now the most precise distance measurement to the Coma cluster. But one can ask, well, um, uh, in the DESI paper, they use the SBF measurement, but Coma's been around. Coma's been measured for a long time. So what did other people get? And I think DESI just kind of used the latest SBF measurement and then kind of called it a day because they didn't want that to be the focus of their paper. But Coma's really been measured a number of times. So this is pretty remarkable. So this is all the measurements of the distance to the Coma cluster, and kind of on this same plot. And this has been measured, as you could see, for decades, and no one has gotten close to what the Planck prediction of the Coma distance should be. So I like people talk often about like blind measurements, and everyone's seen like things could be sort of blind or very blind or whatever. But this is like as blind as you could get because like no one saw this DESI Hubble diagram coming. This is just a cluster that's been measured for decades, and you could see this tension in this kind of very different viewpoint, clear as day. So we can combine independent measurements because a lot of those kind of have various overlap. So the literature mean by itself is about 5 sigma. It kind of takes some like the best ones that are all independent from like JWST using the TRGB, surface brightness fluctuations, ours. So altogether, this is like 4.6 sigma. So I mean, this is a different distance ladder, a using a lot of independent methods, and is kind of pushing the amount of tension that that we see in the shoes team. So I mean, if this thing's on the sky, like this is kind of how it should work, that it shows up in all these ways that you don't expect, and that seems to be what's happening. Okay, so yeah, I think I showed this in my first slide, but this is kind of how it feels like. It's just that the distance that when people measure distances in the local universe, things are just closer. Distances are smaller than a kind of Planck early universe prediction would have it. Um, and I mean, these are relatively simple distance measurements to do. Just this is something that's 100 megaparsecs away, and there hasn't been disagreement about it. Okay. Um, okay. So that is uh, for Coma. On the archive last night, I just put out another new distance ladder measurement. But really, this is like more a revision. So DESI, what they did was fundamental plane. What they'll also do is Tully-Fisher. This is just another um, galaxy kind of standardization distance redshift relation. And the latest paper on and so DESI hasn't released their Tully-Fisher one yet, but there's been a number of papers of Tully-Fisher papers as well. So the latest one was led by Paulo Bubel, and uh, one of the nice things is she compiles all the past Tully-Fisher H-naught measurements, and you can see them here on the right. And I mean the numbers are quite consistent, always like 74, 75. I think I looked in the last like 3 decades, there hasn't been a value less than 70. So kind of similar like story as like the Coma cluster. Okay. But kind of similar to like my reaction of the DESI um, uh, Coma paper, if you look here in the abstract of the paper, they say they get this value, this H-naught value of 73.3 with a relatively small statistical uncertainty, and then a much bigger systematic uncertainty. So to understand kind of how robust this is, but also kind of why is that systematic better, uh, a number of us tried diving into, well, what's driving this systematic uncertainty, and can that be reduced and make this measurement more precise? So uh, the place that this comes from is that just like what I've talked about with DESI and Coma, you need to calibrate that like first or second rung, and then use your distance redshift relation for your last rung. And what you use to do that calibration 0 point will propagate through and can change your value of the Hubble constant. So they use these 2 different samples of Tully-Fisher measurements. One's from SDSS, one's from WISE. You can see WISE has more galaxies in the kind of calibration rung. So in the paper that we put out, we ultimately use WISE. But what you can see here is that like Cepheids and TRGB both give very consistent numbers. Like for WISE is 76.1 for both of them. And then Type Ia Supernovae gives 73.8, which is very far apart. Now, Type Ia Supernovae, they are calibrated by Cepheids or TRGB. So it doesn't really make obvious sense of how, since supernovae are calibrated by those first 2 rows, how they could give a different number. So that was like I don't know, kind of like alarm bell. So that was kind of the main part of the systematic. And then there's another part where they said, um, oh, we have TRGB from a number of literature sources, and then we have this TRGB from Friedman et al. And look, there's this huge difference here, delta H on a 5. But actually, like even some of what Friedman used is in this TRGB. So that part didn't make sense either. So we teamed up with Paula to try to understand this better. Um, and I'll say kind of just before showing it, the short story of it is that um, the supernovae that they used, it was actually calibrated to a Hubble constant of 70. They just took an old paper where 70 was fixed in, and that's what led to their lower value of the Hubble constant. And then this TRGB by Friedman, this actually was not the TRGB of Friedman. It was a misidentified like Cepheid plus combined something set that was just it got a little confused about what that set was. So the SN1A it had a problem that it was H not fixed to 70. The TRGB was just misidentified and shouldn't have been used. So the two things that were driving the systematic just should not have been used in the first place. Okay, so we so we wrote this short note. This is on the archive as of this morning. So if you look at the latest archive listing, where we point out that they get 73.3. But if you take out the two sets that had one that had misidentification, one where H naught was just arbitrarily fixed to 70, then you could go back and just use their CPLR plus TRGB, which gives you this 76.3 plus or minus 2.1. So kind of their best measurement should be this fourth row. And then we spend a lot of time trying to derive kind of what should the systematic be, which we get to be 1.5. So the note goes over kind of these two problems, then kind of tries to kind of, for the record, put across this newer measurement. But really, this is like Paul is the second author. Really, this is just trying to kind of correct these issues to get a cleaner measurement. So one of the reasons that we were excited about it is kind of we've been noticing like this pattern, where and this plot is in the paper where the Pantheon plus shoes, the kind of I don't know most conventional distance ladder, we get a value of 73. And if you then say, all right, use the kind of Cepheid or main TRGB calibration that Shoes uses, and then replace that last rung with not optical Type Ia supernovae. So I've talked so far about Coma, where you're doing that with fundamental plane. I've talked now about this last paper, where you're doing that with Tully-Fisher. There's also been a number of papers that instead of using optical light curves, you're using near-infrared light curves, where you don't have the same dust sensitivity. So that's particularly interesting. There's you could instead of using Type Ia supernovae, which are very standardizable, you use Type II supernovae, which less so, but still interesting. You use surface brightness fluctuations, or you use fundamental plane. This is what I previously talked about. Or now all these Tully-Fisher measurements, where I'm just taking ones that use systematics. The very interesting trend to me is that everything is actually, or just about everything is a little bit higher than our shoes value. So I'm not trying to say like our shoes thing is wrong in any way. That's still I think I don't know maybe like the premier measurement, but this is definitely not indicating like there's any respite for the Hubble tension. If anything, it seems like things are kind of on the local side are pushing you a little higher, 74, 75. But I mean, there's now quite a number of H naught measurements that are in the 74, 75, 76 range. It's pretty kind of I think interesting to see them all together. So for anyone that's trying to like poke at the distance redshift relation, saying maybe there's something there, really swap any of these pieces, and you're gonna get a higher value of the Hubble constant. Okay, so there's another paper last night that came out, also distance ladder related, but I just wanted to say a couple things about it. So this is by Hogus and Mortzel. So besides my Tully-Fisher paper, there's this paper also, if you look on the archive. And they were trying to reanalyze the the distance ladder, and they looked at two separate things. One is trying to measure the Hubble constant for different for Cepheids with different periods, separating the Cepheids into period bins, and then trying to say, is there some kind of signal there that's not been accounted for, and does that move the value of the Hubble constant? So they break this up into the Cepheids that are in the second rung and with the galaxies with supernovae in the first rung, and then they say, okay, for the highest for the Cepheids with the highest periods, you could see possibly this drop. So maybe there's then some structure there that needs to be modeled, and then they try to model it. What's a little confusing about this is that when you measure the value of the Hubble constant, you can't really separate these two rungs. So actually, there's another paper by Kushner and Sharon that tried to do something similar, where they combine those two rungs, and they see deviations, but nothing that looks like they're deviating from the mean. But for the paper last night, they used this to say, okay, well, something is deviating from the mean, so this needs to be modeled. They then add different period luminosity slopes and breaks, so kind of five new parameters, and that ultimately lowers H naught by like point three. It's unclear if this is like a look elsewhere effect, or like for these two bins here, you don't have a number of the supernova hosts, so these could just be like edge effects. Um, in the Kushner-Sharon paper, when they tried to do it, they found it lowered H naught by 0.17, so they said wasn't significant. In shoes, kind of we tried to do something similar. We kind of added one break that lowered H naught by 0.3. But on the other hand, if you took out these higher period guys, that raised H naught by 0.7. So yeah, I don't know. I mean, these are not the biggest numbers, but this is kind of it's important technical analysis, but it kind of unclear if this is kind of helping the cause. Um, the second thing that they do is look at the Milky Way Cepheids, and they say that the likelihood there's in the likelihood there's a normalization term that's possibly missing, and then maybe that changes just for the Milky Way anchor the value of the Hubble constant. It's also possible, just because this came out last night, that there's a count rate nonlinearity that you need to account for. It's unclear if they did. This could change things by 0.03 meg, which this ultimately affects H naught at like the zero point 0.5 kilometers per second per megaparsec level. Um, so there's another paper by Reyes and Anderson, I don't know if Richard's here, where they do it. They saw something zero point 0.3 sigma away from shoes. So kind of again a little unclear. So if they do both of these things, they get 72.4 plus or minus zero point 0.9. But there's more parameters. I think different things are seen by different groups. So I think this is literally, it's only been out for like 12 hours. So these groups need to talk. But to me, this is not like something that's moving the needle too much. I think it shows that shoes is pretty robust. And there's more data coming that will help on this Milky Way part of the analysis. Okay, so that's all distance ladders. I just want to say a couple things before I'm done about like non-distance ladders, because there's been a couple of them lately that I think are pretty interesting. So one that just came out a couple weeks ago is what's called the expanding photosphere method, where this is for type 2 supernovae, but they're using it in this interesting way that for these supernovae, when they explode, the photosphere will get bigger, and you can measure like the velocity of this, and if you could measure temperature, and then you could use the velocity to get the radius, then you could get a luminosity, and then if you could measure brightness, then you could get a distance out. So this is kind of their way of getting a distance, and they make their own kind of Hubble diagrams, but it's like calibrated with no rungs. It's a distance ladder free measurement. So this about at the bottom here is their distance ladder free Hubble diagram. You can see that the it looks quite precise, and they get a value kind of similar to these other high values, the Hubble constant I've been talking about, 74.9 plus minus 1.9, where they say that they think their systematic is comparable to or less than the current statistical uncertainty. So this really has, I'd say, zero overlap with any with like the shoes distance ladder, and and gets a little bit higher value of the Hubble constant. There's another one. This came out last week, and this also like a distance ladder free measurement. Um, so this is particularly interesting and would be my nomination for a CosmoVerse talk. But they do something that Tully has done in his cosmic flow papers, but they do this in terms of pairwise peculiar velocities. They try balancing the inflow and outflow of galaxy velocities, kind of like in and out of halos, and from that they can constrain the Hubble constant, and actually not just the Hubble constant, but they can constrain omega matter pretty well itself. Um, and when doing that, they get a value of the Hubble constant of 75.5 plus or minus 1.4, with actually this relatively precise value of omega matter. So this again, it kind of is just another example of something that has extremely little overlap to the regular distance ladder, but again, giving this like somewhat slightly higher value of the Hubble constant. So just in the last 2 weeks, I think there's been these two very interesting distance ladder free measurements that I encourage people to read. Okay, so let me kind of conclude here, and then I'll be happy to take any questions. In terms of evolving dark energy, I'd say there's still kind of a lot of analysis to do, and particularly I think that it's just more data is needed before people are really jumping on it. I don't think there's anything in the measurements that are people feel are wrong, but it's still there's not enough independent cross checks. With H-naught though, there seems to be a huge number of independent cross checks at this point. There's the Coma distance ladder. This I feel is like a really true blind measurement. Gets a Hubble constant of 76. And I think what's great about this also is that there's going to be a number of new measurements to come. So I don't know if like Deep Ananda's on the call, but there's going to be new SPF measurements, and also there'll be DESI will soon not just calibrate to Coma, but calibrate to other nearby clusters. So this will be, I think, a whole new kind of cottage industry of distance ladder measurements. There's a new Tully-Fisher distance ladder measurement that I talked about. With Tully-Fisher consistently getting around H-naught 75, and I think there's now this bit of this interesting thing of when you use Type Ia Supernovae, are you a little bit on the low side, which is something I feel like a lot of people did not expect. The tension's always going the other way. And I also kind of lastly say I think that there's this rise of no-rung distance ladder that's really promising, and some of the precision they're now reaching is quite interesting. And these would be my nomination for future CosmoVerse talks. So thank you everyone for listening, and happy to take any questions.
Thank you. Very great talk. Nico?
Yeah, sorry. Hi, Dan. A fantastic
Hey,
talk as
Nico.
always. I will save a few questions for January over coffee, but the first one, the only one I'm going to ask here is, if I remember, there's this anchoring points, right, which is very relevant. So does that tie into one of the first slides you were showing of the low Z and high Z sample? So can you explain to me, is it connected to this, like what, because I think you said we need more low Z samples.
Yeah.
But I did not quite understand is why, because I would also assume I can see that the high redshift sample is pushing the H naught towards even higher values. But maybe if you
Right.
can explain that.
Yeah, great. So I don't have a nice Hubble diagram. Sorry, the kind of three rung here, but let me explain it in terms of just like the DS Hubble diagram. So okay, for W or Q naught, W naught, WA, you're measuring this big range of redshifts, and really the leverage is coming from comparing supernova brightnesses at low Z that you can see here to high Z. Um, for H naught, you're really just looking at these low redshift supernovae, but you're comparing these low redshift supernovae to even like lower redshift at Z of like 0.005. So for H naught, you're comparing like very low Z supernovae to low Z supernovae, where just like not much can change. Um, Whereas in like DS, we're comparing these low redshift supernovae to very high redshift supernovae, where you could have evolution or differences in calibration and a number of things that could kind of go wrong. So what I'm advocating for is that in kind of every W analysis, we've used the same low Z sample. I'd like to see this replaced to see kind of how robust it is, because we've now kind of replaced the high redshift part, but we've never replaced the low redshift part.
Because of our ignorance, what happens at redshift 1 evolutionary, right? Is that?
Well,
There's
I
too
mean, we
many
haven't getting
unknowns
higher
there.
just because it's hard to get that high redshift. But yeah, we have multiple samples kind of here, but their statistics are still relatively limited here. So this is the next big thing I'd like to see. Yeah, Adam.
Yeah, if you could put up that slide from that paper from last night you showed on the Cepheids and the periodicity thing.
This
This one.
period.
Oh, yeah, that one. Yeah, I just wanted to emphasize that. I mean, if you look at those 2 points to the right, which is the whole story they're making about, is they're saying, hey, those 2 points to the right, they dip down, therefore there's some structure or complexity in the Cepheid period luminosity relationship, meaning it's not just linear, and we need to model that. But see, I don't think that's the right story, because first of all, you could debate whether those 2 points are, whether those are significant at all. But either way, when I look at the data, I was looking at it while you were giving the talk, like that last data point, there's only 10 galaxies participating in that one far to the right, which is less than a quarter of the sample. And so the fluctuation you see is not because, you have suddenly Cepheids at long periods that you're looking at compared to all the other galaxies at short periods. It's actually that you're looking at 10 galaxies compared to 40, and you're getting a shift from that. And so therefore, even if that's real, that what they're doing wouldn't be the right model. You wouldn't want to say, I'm going to make up a new period luminosity relationship to try to change the way I interpret long period Cepheids, when actually it's those 10 galaxies that you'd want to look at and go, oh, why are those 10 galaxies 2 sigma different than the other 30 galaxies?
Yeah, that's a great point. I see some stuff in the chat. I just want to talk about just like the void for 1 second. So kind of what I was just saying to Nico, one thing that's always been a little hard about Type Ia supernova Hubble diagrams is we have these surveys that look at low redshift, and then we have these kind of higher redshift surveys, and oftentimes we just don't have data kind of in between, like it's just like z greater than 0.1 or so, or is it really like z greater than 0.06? And I think I saw in the chat people talking about like maybe there's like a void that goes to like z of 0.06 and something's going. What one of the things I was most happy about the latest DESI measurements you could see here is that they are crossing that void. So actually, I think they probably make better constraints on voids than supernovae do, and you could just kind of see how smooth this is. There's no like kinks or anything. So I think no one's written this paper yet, but I feel like someone should about new DESI Hubble diagram constraints on voids.
Nico?
I wanted to know maybe your interpretation or your basically how you see it, because the way I see the DESI plots, the famous the deviation from lambda CDM, the way I understand it, it is really truly driven by the supernova samples, right? The supernova data.
Well, I mean, DESI plus Planck, it's like 2.9 sigma, no supernovae. So WA deviation. So I think if to cross 3 sigma, sure, but I don't think the story is just supernovae. There's been a couple papers in the last couple weeks about like trying to nail that down. It's like two of the redshift bins in DESI are driving it, but I do think supernova out of the story, you still have an interesting hint. Is how I put it. But yeah, I feel like my neck is out for the H stuff. Like I'm not ready to do that for the WA. But it's certainly something to watch for right now. Like it deserves the work that people are putting in. Yeah, I think I saw Vivian.
Yeah. Vivian wanted to say something.
Sorry, yes, I was just sorry. Sorry, I was following on and off. So I just had you were mentioning the low redshift supernovae data, and I just wanted to jump on that. What do you have in mind? Is that ZTF that's going to update that?
Yeah,
And
I
when
think
it's coming out?
the two big things are going to be DeBase and ZTF, and I think both in the next year. So,
Okay.
yeah, LSST is coming, but my guess is like three-ish. It turns on in a year, but first Hubble diagram will be 3 or 4 years.
Okay, great. Thank you.
Yeah.
So let's thank Dan again. Thank you so much.
Thank you, everybody.